Hello my friend, welcome back to the Sleepy Professor channel. I'm glad to see you again. Tonight we're going to drift together through the vast, quiet darkness of space, exploring our solar system in all its gentle wonder. There's something deeply calming about the cosmos, isn't there? The way planets turn, slow and silent, tracing their ancient paths. The way moons orbit, patient and constant. The way it all just exists, eternal and beautiful, asking nothing of us but offering everything. For the next little while, just relax, settle into your pillows, let your breathing slow, and let me tell you some wonderful things about this remarkable neighborhood of space we call home. This collection of worlds that have danced together for billions upon billions of years. Get comfortable. There's nowhere you need to be, nothing you need to do. Just listen, and let these cosmic stories carry you gently towards sleep. Let's start with something that sounds almost magical, something that seems impossible. The light you saw from the sun this morning, that warm glow that touched your face, began its journey 8 minutes and 20 seconds earlier. Think about that for a moment. Let it settle in your mind like a soft blanket. The sun is so remarkably far away that even light, which travels at the fastest speed possible in our universe, takes more than 8 minutes to cross that vast emptiness between our star and our world. When you look up at the sun during the day, you're not seeing it as it is right now, in this very moment. You're seeing it as it was 8 minutes ago. It's like receiving a letter from the past, constantly updated, always arriving fresh, a perpetual message from our star telling us it's still there, still burning, still keeping us warm. This means that if the sun were to suddenly vanish, which it won't, please don't worry about that. But if it did, we wouldn't know for 8 minutes and 20 seconds. For those brief moments, we'd still see it, shining in the sky, still feel its warmth on our skin, completely unaware that anything had changed. It's a strange thought, isn't it? A peaceful one in a way. It reminds us that distance in space isn't just measured in miles or kilometers, but in time itself. Every photon of light that touches your eyelids in the morning is a tiny time traveler, and you're standing at the end of its journey. This 8-minute journey doesn't happen in a straight line through nothing though. Each photon of light begins its life deep in the core of the sun, where temperatures reach about 15 million degrees Celsius. But here's something even more remarkable, something that might surprise you. Even though light moves so incredibly fast once it escapes the sun, the journey from the sun's core to its surface takes somewhere between 10,000 and 170,000 years. Yes, years. Imagine that. The light touching your face right now, the light helping you read these words or see the world around you began its existence before human civilization started, before the pyramids were built, before writing was invented. It spent millennia bouncing around inside the sun, ricocheting off atoms, taking random paths, slowly, slowly working its way outward, and only in the last 8 minutes did it finally race across space to reach you. Every sunrise is ancient light finally completing its journey. Every sunset is billions upon billions of photons that started their voyage when mammoths walked the earth. There's something profoundly peaceful about that, isn't there? The sun doesn't rush. It takes its time, and yet it's always there, always constant, always reliable. Speaking of the sun, let's stay with our star for a moment, because it holds so many gentle secrets. The sun is so large that you could fit about 1.3 million Earths inside it. Not side by side, not arranged neatly, but actually contained within its volume. Imagine our entire world, every mountain and ocean, every city and forest, every person and creature, multiplied 1.3 million times, and all of it fitting inside that glowing ball we see in the sky. It's difficult for our minds to grasp that kind of scale, and that's okay. You don't need to understand it completely. Just let the vastness wash over you like a warm wave. The universe is big, so wonderfully, impossibly big, and we're small, and there's something deeply comforting about that. The sun makes up 99.86% of all the mass in our solar system. Everything else, all the planets, all the moons, all the asteroids and comets, all the dust and gas floating in the darkness, all of that together accounts for just 0.14%. The sun is, in the most literal sense, almost everything. We orbit around it, we depend on it, we exist because of it, and yet it asks nothing in return. It simply shines, as it has for 4.5 billion years, as it will continue to do for another 5 billion years or so. There's patience in that. Cosmic patience. The kind of patience that makes our human worries seem very small and very temporary. The sun rotates, did you know that? It spins on its axis just like Earth does, but because it's not a solid object, different parts of it rotate at different speeds. The equator of the sun completes a rotation about every 24 to 25 days, while the polar regions take closer to 35 days. It's like a giant ball of honey slowly turning in space, the middle moving faster than the top and bottom. This differential rotation creates complex magnetic fields, twisting and tangling like invisible threads, and these fields are responsible for sunspots, solar flares, and the beautiful auroras that sometimes dance across our night skies near the poles. But even these dramatic events, these explosions of energy that seem so violent, happen in slow motion from our perspective. The sun's changes unfold over days and weeks and years, never rushed, always following the ancient rhythms of physics and magnetism. Every second, the sun converts about 600 million tons of hydrogen into helium through the process of nuclear fusion. That's happening right now as you rest here, listening to these words, 600 million tons every single second. And this process, this transformation, releases the energy that becomes light and heat. The energy that warms our planet, that drives our weather, that makes plants grow, that makes life possible. The sun is the most generous thing in our solar system, constantly giving away its energy, constantly sharing its light, never asking for anything back. It's been doing this for so long that it's converted about half of its hydrogen into helium already, and yet it still has enough fuel to continue for billions of years more. There's no need to worry, no need to think about endings. The sun will outlive us, our children, our children's children, on and on through generations we can't even imagine. It's eternal in any time frame that matters to us. Let's drift away from the sun now, moving gently through space, heading toward the first planet in our solar system. Take a deep breath. Feel yourself floating, weightless, peaceful, moving at your own pace through the darkness. Mercury is the closest planet to the sun, and it's a world of extremes. But even extremes can be soothing when you hear about them from a comfortable distance. During the day on Mercury, temperatures can reach 430 degrees Celsius, hot enough to melt lead. but at night temperatures plummet to minus 180 degrees Celsius. That's a difference of more than 600 degrees between day and night, the largest temperature variation of any planet in our solar system. Why such extremes? Because Mercury has almost no atmosphere to trap heat and distribute it around the planet. When the sun shines on Mercury's surface, that surface absorbs the heat directly, intensely. When the sun sets, that heat radiates back into space immediately, and the temperature drops dramatically. It's a world of harsh contrasts, but from here, from the safety and comfort of Earth, it's just another fascinating detail in our cosmic story. Mercury is small, only slightly larger than Earth's moon, and it takes just 88 Earth days to complete one orbit around the Sun. That means a year on Mercury is only 88 days long. But here's something curious, something that shows how strange and wonderful planetary mechanics can be. One day on Mercury, one complete rotation on its axis, takes about 59 Earth days. So a day on Mercury is about 2/3 as long as a year on Mercury. Imagine that. You'd have a sunrise, and then 59 days would pass before noon arrived, and another 59 days before sunset, and by then you'd have gone around the sun more than once. Time works differently there. Days and years interweave in a slow, strange dance that's nothing like what we experience here. Mercury is covered in craters, scars from billions of years of impacts from asteroids and comets. One of the largest is called the Caloris Basin, a massive impact crater about 1,550 kilometers in diameter. When the object that created this crater struck Mercury, the impact was so powerful that it sent shockwaves through the entire planet. On the exact opposite side of Mercury from the Caloris Basin, you can find strange jumbled terrain, hills and valleys created when those shockwaves converged on that one point. The entire planet rang like a bell from that ancient impact. It happened billions of years ago, and yet the evidence remains, frozen in stone and dust, a permanent record of one violent moment in the early solar system. But that moment is long past. Mercury is quiet now, silent, slowly turning in its strange rhythm, closest to the sun, bathed in light and heat, alone with its craters and its memories. Despite being so close to the sun, Mercury has ice. Yes, ice. This seems impossible at first, given the searing temperatures on the day side, but Mercury's axial tilt is nearly zero, which means the sun never rises high in the sky at the poles. Deep craters at Mercury's poles have floors that never see sunlight, regions of permanent shadow where temperatures remain cold enough for water ice to exist. Radar observations from Earth and data from the Messenger spacecraft that orbited Mercury confirmed the presence of this ice, hiding in the shadows, protected from the sun's heat by nothing more than the walls of ancient craters. There might even be organic compounds mixed with the ice, delivered by comets that crashed into Mercury billions of years ago. It's a reminder that even the most extreme environments can have hidden pockets of gentleness, places where the rules seem to bend, where the unexpected becomes possible. Let's move outward, drifting past Mercury, heading toward a world much more familiar to us, a world we often call Earth's sister planet. Venus is the second planet from the Sun, and it's the brightest natural object in our night sky after the moon. You've probably seen it many times without even realizing it was a planet. It appears in the evening sky after sunset, which is why it's sometimes called the evening star, or in the morning sky before sunrise when it's called the morning star. But it's not a star at all. It's a planet, our neighbour, shining so brightly because its thick clouds reflect sunlight beautifully. Venus is about the same size as Earth, which is why astronomers once thought it might be similar to our world in other ways too. But Venus is very, very different. The atmosphere of Venus is so thick, so incredibly dense, that the pressure on its surface is about 92 times greater than the pressure at sea level on Earth. If you could stand on Venus, which you can't because it's far too hot and the pressure would crush you instantly, but if you could, it would feel like being a kilometre underwater in Earth's oceans, the weight of all that atmosphere. Pressing down would be immense, and that atmosphere is made almost entirely of carbon dioxide, with clouds of sulfuric acid. Sulfuric acid clouds. It sounds terrifying, doesn't it? But remember, you're here, safe and comfortable, just listening to stories about distant worlds you'll never have to visit. Because of this thick atmosphere and the greenhouse effect it creates, Venus is the hottest planet in our solar system, even though Mercury is closer to the Sun. The surface temperature on Venus averages around 465 degrees Celsius, hot enough to melt lead, hot enough to glow a dull red if you could see through the clouds. The heat is constant, the same temperature day and night, at the equator and at the poles. The thick atmosphere distributes heat so efficiently that there's barely any variation. It's a planet locked in an eternal furnace, and yet from Earth, when we look up at Venus in the evening or morning sky, it appears as a beautiful, brilliant point of light, serene and lovely. We see only its clouds, reflecting sunlight, hiding the hostile world below. Sometimes the most beautiful things from a distance are the most dangerous up close, and sometimes that's perfectly fine. We can admire Venus from here, appreciate its brightness, and never need to go any closer. Venus rotates very, very slowly, and it rotates in the opposite direction from most planets in the solar system. This is called retrograde rotation. While Earth and most other planets rotate counterclockwise when viewed from above the North Pole, Venus rotates clockwise. Why? No one knows for certain. Perhaps it was struck by a massive object early in its history, knocking it into this unusual rotation. Perhaps tidal forces from the Sun gradually slowed and then reversed its spin over billions of years. It remains a mystery, one of many in our solar system, and mysteries are good things. They remind us that we don't have all the answers, that there's still wonder left in the universe, still things to discover and ponder. One day on Venus, one complete rotation, takes about 243 Earth days. A year on Venus, one orbit around the Sun, takes about 225 Earth days. So a day on Venus is actually longer than a year on Venus. Think about that for a moment. You could celebrate your birthday before the sun set for the first time. The sun rises in the west on Venus because of its retrograde rotation, not in the east like on Earth, and it moves so slowly across the sky that if you could see it through the clouds, which you can't, but if you could, you'd barely notice it moving at all. Time on Venus is stretched out, elongated, dreamlike. A single day lasts for months. There's something almost peaceful about that, despite the hellish conditions. Time moves at its own pace, unrushed, unconcerned with our human sense of urgency. The clouds of Venus are layered, thick and opaque, extending from about 45 to 70 kilometers above the surface. These clouds are made of sulfuric acid, droplets, and they race around the planet in what's called superrotation, completing a circuit around Venus in just 4 Earth days, even though the planet itself takes 243 days to rotate once. Winds in the upper atmosphere reach speeds of 360 kilometers per hour, driven by poorly understood mechanisms. The lower atmosphere is much calmer, with gentle breezes near the surface, but the pressure and heat make it irrelevant whether the wind is blowing or not. Everything is equally hostile. In the 1960s through the 1980s, the Soviet Union sent a series of spacecraft called Venera to Venus. Several of them successfully landed on the surface and transmitted data back to Earth, before succumbing to the heat and pressure. Venera 13 holds the record for longest survival on Venus's surface, lasting 127 minutes before failing. In that time, it sent back the first colour images of Venus's surface, showing flat rocky plains littered with basalt-like rocks under an orange sky. The images are eerie and alien, a glimpse of a world where nothing from Earth could survive for long, and yet there it is, real and solid, a place you could theoretically stand if only you could withstand the conditions. Those Venera landers are still there on Venus, silent now, slowly being corroded by the heat and acid, monuments to human curiosity and ingenuity. Now let's come home for a moment. Let's talk about Earth, our world, the pale blue dot that holds everything we've ever known. Earth is the 3rd planet from the Sun, sitting right in what scientists call the habitable zone, the region around a star where temperatures are just right for liquid water to exist on a planet's surface. Not too hot, not too cold, just right. And water is essential for life as we know it. Earth is about 4.54 billion years old, formed from the same cloud of gas and dust that created the Sun and all the other planets. For the first several 100 million years, Earth was a hellish place, constantly bombarded by asteroids and comets, its surface molten, its atmosphere toxic. But gradually, over immense periods of time, it cooled. Water vapor condensed and fell as rain that lasted for millions of years, filling the basins that became our oceans. The atmosphere changed as early life began to produce oxygen. Continents formed and shifted. Ice ages came and went. And eventually, billions of years after it formed, Earth became the world we know today. A world covered in water and life. The only place in the entire universe where we know for certain that life exists. About 71% of Earth's surface is covered by water. The oceans contain about 1.335 billion cubic kilometers of water. That's an almost incomprehensible amount. All that water, all those waves and currents and tides, constantly moving, constantly flowing, driven by the moon's gravity and the sun's heat and the Earth's rotation. The deepest part of the ocean, the Mariana Trench, reaches down about 11 kilometers below sea level. If you took Mount Everest, the tallest mountain on Earth, and placed it at the bottom of the Mariana Trench, its peak would still be covered by over 2 kilometers of water. The ocean is deep, so wonderfully deep, and we've explored only a small fraction of it. There are creatures down there, in the darkness, that have never seen sunlight, that have never been seen by human eyes. There are underwater mountains and valleys, plains and ridges, an entire landscape hidden beneath the waves. The ocean is like another world, right here on our own planet, filled with mysteries and wonders. Earth's atmosphere is a miracle of chemistry and physics. It's about 78% nitrogen and 21% oxygen, with trace amounts of argon, carbon dioxide, and other gases. That oxygen is special. It didn't exist in Earth's early atmosphere. It was created by living organisms, primarily cyanobacteria, through the process of photosynthesis. These tiny organisms converted carbon dioxide and water into organic compounds and oxygen as a byproduct. Over hundreds of millions of years, oxygen accumulated in the atmosphere, eventually reaching levels high enough to support complex life. This event is called the Great Oxidation Event, and it happened about 2.4 billion years ago. It was one of the most important transformations in Earth's history, making possible all the oxygen-breathing life that exists today, including us. We breathe the waste product of ancient bacteria. Every breath you take connects you to billions of years of life on Earth, to countless generations of organisms that came before you, transforming the world bit by bit. Earth has one moon, just one, and it's been our companion for about 4.5 billion years, almost as long as Earth itself has existed. The leading theory for how the moon formed is that early in Earth's history, a Mars-sized object called Theia collided with our planet. The impact was catastrophic, unimaginably violent, ejecting huge amounts of material into orbit around Earth. This debris gradually coalesced, pulled together by gravity, forming the moon. So the moon is, in a sense, a piece of Earth, a remnant of that ancient collision, forever orbiting us, forever connected to us. It's a companion born from disaster, from destruction, and yet it's become something beautiful, something that lights our night sky, something that pulls our oceans into tides, something that has inspired countless poems and songs and stories throughout human history. The moon is slowly drifting away from Earth at a rate of about 3.8 centimeters per year. It's not much, barely noticeable in a human lifetime, but over millions and billions of years, it adds up. The moon used to be much closer. Early in Earth's history, the moon appeared much larger in the sky, and its gravitational influence was stronger, creating massive tides that might have sloshed water hundreds of kilometers inland. Days were shorter back then too, because Earth was rotating faster. The moon's gravity has been gradually slowing Earth's rotation, lengthening our days bit by bit. About 600 million years ago, a day on Earth was only about 22 hours long. About 1.4 billion years ago, a day was only 18 hours, and the process continues. Billions of years from now, if Earth and the moon both still exist, they will become tidally locked, meaning Earth will rotate only once per orbit of the moon, and one side of Earth will always face the moon, just as one side of the moon already always faces Earth. But this won't happen for billions of years, so there's no need to worry about it. It's just another example of how everything in space is constantly changing. Slowly, gradually, patiently. The moon's influence on Earth is more profound than you might think. Those tides it creates aren't just interesting phenomena, they're essential to life on Earth. Tides mix nutrients in coastal waters, create unique ecosystems in tidal zones, and may have played a role in helping early life transition from sea to land. The moon also stabilizes Earth's axial tilt. Without the moon, Earth's tilt would vary wildly over time due to gravitational influences from other planets, causing dramatic climate swings that would make it difficult for complex life to evolve. The moon keeps us steady, keeps our seasons regular, keeps our climate relatively stable. It's a guardian, in a way, silently protecting us from chaos. Here's something that might help you sleep tonight. Right now, as you lie in bed, you're moving through space at incredible speeds, and yet you feel perfectly still. Earth rotates on its axis at about 1,670 kilometers per hour at the equator. That's the speed at which the ground beneath you is spinning. But you don't feel it, because the atmosphere moves with us, because everything is moving together, smoothly, consistently. At the same time, Earth is orbiting the Sun at about 107,000 kilometers per hour. That's our speed through space as we circle our star. And the Sun itself, along with the entire solar system, is moving through the Milky Way galaxy at about 720,000 kilometers per hour. And the Milky Way is moving through space toward the Virgo supercluster at about 2.1 million kilometers per hour. You are traveling through the universe at millions of kilometers per hour, and yet you can lie perfectly still in your bed, comfortable and safe, because motion is relative, because everything is moving together. There's something profound about that, something that makes our everyday problems seem less heavy. We are cosmic travelers, all of us, whether we realize it or not. Earth's magnetic field is another invisible guardian, protecting us from harmful radiation from the Sun. The field is generated by the motion of molten iron in Earth's outer core, creating a dynamo effect. This magnetic field extends far into space, creating a region called the magnetosphere that deflects most of the charged particles in the solar wind, preventing them from reaching Earth's surface. Without this magnetic field, the solar wind would gradually strip away Earth's atmosphere, as it has done on Mars, which lost its magnetic field billions of years ago. The magnetic field also creates the auroras, those beautiful lights that dance across the sky near the poles when charged particles from the Sun interact with gases in our atmosphere. The aurora borealis in the northern hemisphere and the aurora australis in the southern hemisphere are visible manifestations of our planet's protective shield, glowing curtains of green and red and purple light rippling across the darkness. Let's journey outward again, moving past Earth, heading toward the red planet that has captured human imagination for centuries. Mars is the fourth planet from the Sun, and it's the planet in our solar system that's most like Earth, though that's not saying much. Mars is cold, dry, and has an atmosphere that's only about 1% as thick as Earth's. But it has similarities to our world that make it fascinating. Mars has polar ice caps, just like Earth, made of water ice and carbon dioxide ice. It has seasons, because its axis is tilted at about the same angle as Earth's. It has mountains and valleys, canyons and plains. It even has weather, though it's much different from Earth's weather. Dust storms on Mars can grow so large that they envelop the entire planet, turning the sky hazy and dim for months at a time. These global dust storms happen every few Martian years, and they're something to behold, even though no human has ever seen one in person. Mars is home to Olympus Mons, the tallest planetary mountain in our solar system. It's a shield volcano, similar in structure to the volcanoes in Hawaii, but incomparably larger. Olympus Mons rises about 25 kilometers above the surrounding plains. That's nearly 3 times the height of Mount Everest. The base of Olympus Mons is about 600 kilometers in diameter. If you stood at the center of its base and looked toward the edge would be beyond the horizon. The volcano is so large that its slopes are very gentle, only about 5 degrees on average. If you were climbing it, you might not even realize you were on a mountain. You'd just be walking up a very gradual, very long slope that went on for hundreds of kilometers. And if you reached the summit, you'd be standing in space, essentially, because the peak of Olympus Mons rises above most of Mars' thin atmosphere. You could look up and see stars in the daytime because there would be so little air above you to scatter sunlight. It would be a lonely, magnificent place, silent and still, the highest point on Mars, a monument to the volcanic forces that shaped the planet billions of years ago. Mars also has the largest canyon in the solar system, Valles Marineris. This enormous rift valley stretches about 4,000 kilometers long, up to 600 kilometers wide in places and up to 8 kilometers deep. To put that in perspective, it's about as long as the entire United States from coast to coast. The Grand Canyon on Earth, which seems so vast when you stand at its rim, is tiny in comparison. Valles Marineris is so deep that if you stood at the bottom and looked up, the walls would tower over you, blocking out much of the sky. It's thought to have formed billions of years ago as the Tharsis region, a massive volcanic plateau, swelled upward and caused the crust of Mars to crack and collapse in this region. But it might also have been shaped by flowing water in Mars' ancient past, carved and widened by rivers that no longer exist. Mars once had liquid water on its surface, we think. Not now, not anymore, but billions of years ago Mars might have been warmer, wetter, more hospitable. Rivers might have flowed, lakes might have formed, and who knows, life might have existed there too. But if it did, it's gone now, or hidden deep underground, and Mars is left cold and dry, a monument to a lost past. The surface of Mars is red because of iron oxide, which is just rust. The entire planet is covered in a fine dust that contains oxidized iron, and when sunlight hits this dust, it reflects back a reddish color. That's why Mars appears red to us. Why ancient civilizations associated it with blood and war. Why we call it the Red Planet. But if you were standing on Mars looking around, the sky wouldn't be blue like on Earth. During the day, the Martian sky is a butterscotch colour, a tawny yellowish brown, because the dust particles in the thin atmosphere scatter light differently than the molecules in Earth's atmosphere. At sunset, though, something beautiful happens. While sunsets on Earth are red and orange and pink, sunsets on Mars are blue. The sun appears as a small bluish disk sinking toward the horizon, surrounded by a blue glow. It's the opposite of Earth, a strange and lovely inversion. Blue sunsets on a world of red dust. The universe is full of these unexpected beauties. Mars has 2 small moons, Phobos and Deimos, named after the Greek gods of fear and dread who accompanied Ares, the god of war, into battle. But there's nothing fearsome about these moons. They're tiny, irregularly shaped, probably captured asteroids rather than moons that formed alongside Mars. Phobos is the larger of the two, about 22 kilometers across at its widest point. It orbits so close to Mars, only about 6,000 kilometers above the surface, that it completes 3 orbits every Martian day. If you stood on Mars and watched Phobos, you'd see it rise in the west, move across the sky in about 4 hours, and set in the east, then do it all over again. And Phobos is getting closer to Mars over time, spiralling inward, and in about 50 million years it will either crash into Mars or break apart and form a ring around the planet. 50 million years is a long time though. There's no rush. These things happen slowly, on timescales that make human history look like the blink of an eye. Deimos is even smaller than Phobos, only about 12 kilometers across. It orbits farther from Mars, taking about 30 hours to complete one orbit. From the surface of Mars, Deimos would appear as a very bright star, not really looking like a moon at all because it's so small and so distant. Both Phobos and Deimos are heavily cratered, dark, and covered in regolith, the dusty layer of pulverized rock that accumulates on airless bodies over billions of years of impacts. They're ancient witnesses to the history of Mars, silently orbiting, holding secrets in their cratered surfaces about the early solar system. Scientists have been studying Mars intensely for decades, sending rovers and orbiters to explore its surface and atmosphere. The rovers, like Spirit, Opportunity, Curiosity, and Perseverance, have travelled across Mars, drilling into rocks, analysing soil, taking thousands of photographs. They've found evidence of ancient river, valleys, lake beds, and minerals that form in the presence of water. They've detected organic molecules, the building blocks of life, though not life itself. They've measured radiation levels, tested the soil chemistry, and sent back data that helps us understand what Mars was like billions of years ago, and what it might take for humans to one day visit or even live there. One of the most intriguing discoveries is that Mars still has liquid water, not on the surface, but underground. Radar data from orbiting spacecraft suggest there may be a lake of liquid water beneath the southern polar ice cap, kept liquid by salts dissolved in it that lower its freezing point, similar to how salt is used to melt ice on roads in winter. If there's liquid water on Mars, even deep underground, then there's a possibility, however slim, that microbial life might exist there, adapted to the cold and darkness and isolation. It's just a possibility, not a certainty, but it's enough to fuel our imagination and our curiosity. Now we reach a boundary in our solar system, an invisible line between the rocky inner planets and the giant outer planets. Between Mars and Jupiter lies the asteroid belt, a region filled with millions of chunks of rock and metal, leftovers from the formation of the solar system. These are pieces that never came together to form a planet, prevented from doing so by Jupiter's powerful gravity stirring things up. The asteroid belt sounds dangerous, like something from a science fiction movie where spaceships have to dodge and weave through a dense field of tumbling rocks. But in reality, the asteroid belt is mostly empty space. The asteroids are spread out over such an enormous volume that if you flew a spacecraft through the belt, you probably wouldn't even see an asteroid with your naked eye. They're far apart, each one travelling in its own lonely orbit, separated from its neighbours by millions of kilometres. It's a quiet place, the asteroid belt, cold and dark and peaceful. The largest object in the asteroid belt is Ceres, which is actually classified as a dwarf planet now. Ceres is about 940 kilometres in diameter, making it by far the biggest thing between Mars and Jupiter. It's roughly spherical, pulled into a round shape by its own gravity, and it contains about a third of the total mass of the entire asteroid belt. But even Ceres is tiny compared to the planets. It's only about the size of Texas. Still, It's fascinating. Recent observations from the Dawn spacecraft, which orbited Ceres from 2015 to 2018, suggest that Ceres might have a subsurface ocean of liquid water beneath its icy crust, or at least pockets of briny liquid. Water on a dwarf planet is the asteroid belt. It's a reminder that the solar system is full of surprises, that even in places we think of as dead and lifeless, there might be hidden depths, hidden possibilities. Dawn also discovered bright spots on Ceres, patches that reflect much more light than the surrounding dark surface. These turned out to be deposits of sodium carbonate, a type of salt, likely left behind when briny water from the interior seeped up to the surface and evaporated. In one crater, called a Cater crater, there's a particularly bright deposit that's thought to be recent. Geologically speaking, perhaps only a few million years old. This suggests Ceres might still be geologically active, that there might still be processes moving material from the interior to the surface. It's a small, cold world far from the sun, and yet it's not entirely dead. There's a kind of stubborn persistence to that, isn't there? Even in the cold and darkness, things keep happening slowly but surely. Asteroids come in different types based on their composition. Some are made mostly of metal, primarily iron and nickel. These are called M-type asteroids, and they're thought to be fragments of the cores of larger objects that were shattered by collisions billions of years ago. Some asteroids are made mostly of rock, silicate minerals similar to what you'd find on Earth. These are S-type asteroids, and some are dark and carbon-rich, called C-type asteroids, which are thought to be some of the most primitive objects in the solar system, largely unchanged since they formed. Studying asteroids helps us understand the building blocks of planets, the conditions in the early solar system, and the processes that shaped our cosmic neighborhood. Some asteroids pass close to Earth, and astronomers keep a careful watch on these near-Earth objects. Most pose no threat, but occasionally one comes close enough that we take notice. In 2013, an asteroid exploded over Chelyabinsk, Russia, as we mentioned earlier, reminding us that space is not entirely empty and that Earth is still being bombarded, albeit mostly by small objects that burn up in the atmosphere. Larger impacts are much rarer, happening once every few million years, but they can be catastrophic when they do occur. The asteroid that struck Earth 66 million years ago, creating the Chicxulub crater in what is now Mexico, is thought to have caused the extinction of the dinosaurs and many other species. It was about 10 kilometers in diameter, and its impact released energy equivalent to billions of nuclear bombs, throwing so much dust and debris into the atmosphere that sunlight was blocked for years, causing global winter. But events like that are extraordinarily rare, and we're now capable of detecting and potentially deflecting dangerous asteroids long before they pose a threat. The universe can be dangerous, but it's also predictable, and with knowledge comes the ability to protect ourselves. Let's drift outward now, beyond the asteroid belt toward the giant planets, the worlds so large they make Earth look like a pebble. Take a deep breath. Feel yourself floating, calm and relaxed, moving through the vastness of space. Jupiter is the fifth planet from the Sun and the largest planet in our solar system by far. It's so massive that all the other planets in the solar system could fit inside it with room to spare. Jupiter contains more than twice the mass of all the other planets combined. It's a giant, a king among planets, and yet it's not solid. Jupiter is a gas giant, made mostly of hydrogen and helium, the same elements that make up the Sun. If you could somehow descend into Jupiter, you wouldn't find a surface to stand on. You'd just sink deeper and deeper into increasingly dense gas, the pressure growing, the temperature rising, until eventually the hydrogen around you would be compressed so much that it would start behaving like a liquid metal. At the very center of Jupiter, there might be a solid core of rock and ice, but we're not certain. It's difficult to study the interior of a planet when there's no way to dig into it, no way to send a probe down through thousands of kilometers of crushing atmospheric pressure. Jupiter's most famous feature is the Great Red Spot, a storm larger than Earth that has been raging for at least 350 years, possibly much longer. When astronomers first pointed telescopes at Jupiter in the 1600s, they noticed this oval red spot on the planet's surface, and it's been there ever since, slowly changing size and shape, drifting around in latitude but never disappearing. The Great Red Spot is an anticyclonic storm, meaning it rotates counterclockwise in the southern hemisphere, the opposite direction of hurricanes on Earth. Wind speeds at its edges can reach up to 680 kilometers per hour. The storm is so large that 3 Earths could fit inside it side by side. And yet, despite its size and power, it's gradually shrinking. Observations over the past century show that the Great Red Spot is getting smaller, though no one knows why. Perhaps in another century or two it will finally dissipate, and Jupiter's face will look different. But for now it continues, a swirling red eye staring out at the cosmos, storm that has outlasted civilizations on Earth. Jupiter rotates faster than any other planet in our solar system. Despite its enormous size, it completes one rotation in just under 10 hours. That means a day on Jupiter is only about 10 hours long. This rapid rotation causes Jupiter to bulge at its equator. It's not perfectly spherical, but rather an oblate spheroid, wider at the middle than at the poles. If you measured the diameter from pole to pole and compared it to the diameter at the equator, there would be a difference of about 9,000 kilometers. Jupiter is spinning so fast that it's literally flinging itself outward at the middle. And this rapid rotation also creates powerful jet streams in Jupiter's atmosphere. Winds that blow at hundreds of kilometers per hour, organized into bands that circle the planet. These bands are visible through telescopes as alternating light and dark stripes, zones and belts they're called, and they're incredibly stable, persisting for decades or centuries. The dynamics of Jupiter's atmosphere are complex and beautiful, a lesson in fluid mechanics on a planetary scale. The Juno spacecraft has been orbiting Jupiter since 2016, and it's sent back stunning images and data about the planet. Juno's close flybys have revealed that Jupiter's poles look nothing like the rest of the planet. While the equatorial regions have those familiar banded stripes, the poles are covered in enormous cyclones arranged in geometric patterns. At the North Pole, there's a central cyclone surrounded by 8 others, all swirling together like a cosmic flower. At the South Pole, there are 5 cyclones arranged around a central one. These cyclones are massive, each one larger than Earth's largest hurricanes, and they're stable, persisting for years. No one expected to see anything like this, and scientists are still trying to understand what creates and maintains these patterns. Jupiter continues to surprise us even after centuries of observation. Jupiter has at least 95 known moons, and more are being discovered regularly as our telescopes improve. The 4 largest moons of Jupiter are called the Galilean moons, as they were discovered by Galileo Galilei in 1610 when he pointed his telescope at Jupiter. Their names are Io, Europa, Ganymede, and Callisto, and each one is a world unto itself, unique and fascinating. Let's talk about them for a while, because they're some of the most interesting places in our solar system. Io is the innermost of the Galilean moons, and it's the most volcanically active body in the entire solar system. Io's surface is constantly being resurfaced by volcanic eruptions, which eject plumes of sulfur and sulfur dioxide hundreds of kilometers into space. These volcanoes are powered not by radioactive decay in Io's interior, like volcanoes on Earth, but by tidal heating. Jupiter's immense gravity pulls on Io, and the other Galilean moons also tug on Io as they pass by, and these gravitational forces squeeze and stretch Io like a stress ball, generating friction and heat in its interior. That heat has to go somewhere, so it escapes through volcanoes. Hundreds of volcanoes, constantly erupting, constantly changing the landscape. Io is yellow and orange and red and white, coloured by sulfur compounds on its surface, and it looks like nothing else in the solar system, like a cosmic pizza, some say, though that comparison doesn't do it justice. Io is alien, truly alien, a world of fire and sulfur where the ground is constantly moving, constantly melting, constantly renewing itself. Despite the violent volcanic activity, there's something almost serene about Io when you think about it. It's been erupting constantly for billions of years, and it will continue for billions more. The volcanoes aren't random or chaotic. They're the result of predictable gravitational forces, mathematical and precise. Io is in a state of balance, its heat output matching its heat input, forever in motion, forever changing, and yet forever the same. It's a kind of dynamic equilibrium, a dance that never ends. Europa, the second Galilean moon, is covered entirely in ice. Its surface is one of the smoothest in the solar system, with very few craters, suggesting that it's geologically active and young in geological terms. But beneath that ice, something extraordinary might exist. Scientists believe that Europa has a global ocean of liquid water beneath its icy crust, an ocean that might be more than 100 kilometers deep. That's deeper than any ocean on Earth. The ice above this ocean is probably tens of kilometers thick, but cracks and ridges on the surface suggest that the ice is constantly shifting and breaking, possibly allowing water from below to reach the surface occasionally. And if there's liquid water, and if there's heat from tidal forces like on Io, and if there are chemicals dissolved in that water, then perhaps, just perhaps, life could exist in Europa's ocean. Not intelligent life, probably, but simple organisms, microbes, things that could live in the darkness far from the sun, using chemical energy instead of sunlight. It's speculation, but it's informed speculation, and future missions to Europa might one day answer this question. For now, Europa remains a mystery, a frozen world that might harbour a secret ocean, a place where life could exist far from the warmth of the sun. The surface of Europa is crisscrossed with long linear features called lineae, which are cracks in the ice. Some of these cracks are reddish-brown, thought to be stained by salts or sulfur compounds from the ocean below. In some places, the ice appears to have broken apart and refrozen in new configurations, creating regions called chaos terrain, where jumbled blocks of ice are frozen in place like a puzzle that's been taken apart and reassembled wrong. All of this suggests that Europa's ice shell is dynamic, that it moves and cracks and reforms driven by the ocean beneath. And occasionally plumes of water vapour have been detected erupting from Europa's surface, shooting up hundreds of kilometres into space. If these plumes are real, and if they come from the subsurface ocean, then we might be able to study Europa's ocean without even landing on the surface, just by flying through the plumes and analysing the water vapour and any particles it carries. It's an exciting possibility, and missions are being planned to do exactly that. Ganymede is the third Galilean moon, and the largest moon in the solar system, even bigger than the planet Mercury. Ganymede is a strange mix of rock and ice, with a surface that shows both very old, heavily cratered terrain and younger, grooved terrain that suggests geological activity at some point in its past. Ganymede is the only moon in the solar system known to have its own magnetic field, which suggests it has a liquid iron core generating that field through a dynamo effect similar to Earth and like. Europa, Ganymede might also have a subsurface ocean, though it would be buried much deeper beneath multiple layers of ice and water. Ganymede is quiet now, geologically speaking, but it holds clues to its more active past, and it might hold hidden oceans as well. The grooved terrain on Ganymede is fascinating. It consists of parallel ridges and valleys that stretch for hundreds of kilometres, thought to have formed when the moon's icy crust was stretched and fractured by tectonic forces. Some of these grooves are younger than others, suggesting multiple episodes of geological activity over Ganymede's history. The older terrain is dark and heavily cratered, saturated with impact scars from billions of years of bombardment. The contrast between the old and new terrain is stark, like looking at two different worlds side by side on the same moon. Ganymede is a moon with a complex past, and it's still revealing its secrets to us. Callisto is the fourth Galilean moon, the outermost of the four, and it's the most heavily cratered object in the solar system. Its surface is ancient, unchanged for billions of years, covered in impact scars that record the violent early history of the solar system. Callisto seems dead, geologically inactive, but it too might have a subsurface ocean, detected through measurements of its magnetic field. The ocean, if it exists, would be buried beneath hundreds of kilometers of ice, isolated from the surface, a hidden sea in a frozen world. Callisto is quiet and patient, a witness to the passage of time, a reminder that not everything changes quickly. Some things remain, enduring, constant through the ages. So all four Galilean moons, despite their differences, might have liquid water hidden beneath their surfaces. It's a remarkable thought. Jupiter doesn't just have moons, it has a system of worlds, some active and volcanic, some frozen and mysterious, some possibly harbouring oceans where life might exist. And all of them are locked in an intricate gravitational dance around their giant parent planet, forever orbiting, forever influenced by Jupiter's massive presence. Jupiter has dozens of smaller moons as well, many of them tiny and irregular, probably captured asteroids or remnants of larger moons that were shattered by impacts. Some orbit very far from Jupiter, taking years to complete a single orbit. Some orbit in retrograde, going the opposite direction from Jupiter's rotation. These small moons are barely known, barely studied, but they're part of the Jupiter system, part of the family, each with its own story. Jupiter also has a faint ring system, discovered by Voyager 1 in 1979. The rings are made of dust, probably kicked up from Jupiter's small inner moons by micrometeorite impacts. The rings are thin and faint, not nearly as spectacular as Saturn's, but they're there, encircling the giant planet, a delicate halo of dust and ice. Jupiter acts as a cosmic guardian for the inner solar system. It's powerful. Gravity attracts and captures many comets and asteroids that might otherwise threaten Earth. Jupiter has been struck by comets in recent history. In 1994, comet Shoemaker-Levy 9 broke apart and crashed into Jupiter, creating massive impact scars in the planet's atmosphere that were visible from Earth. Jupiter took the hit for us, so to speak, absorbing objects that could have caused devastation if they'd struck Earth instead. It's a protector, this giant planet, quietly keeping the inner solar system safer through its gravitational influence. Now let's continue our journey outward, drifting beyond Jupiter, deeper into the outer solar system where the sun's light grows dimmer and the cold deepens. We're approaching Saturn, the jewel of the solar system, the planet famous for its stunning rings. Saturn is the 6th planet from the Sun and the 2nd largest in our solar system. Like Jupiter, it's a gas giant, made mostly of hydrogen and helium with no solid surface. Saturn is less dense than Jupiter, though. In fact, Saturn is the least dense planet in our solar system. Its average density is less than water, which means that if you could find a bathtub large enough, Saturn would float in it. Imagine that. A planet so large you could fit over 760 Earths inside it, and yet it would float. There's something delightfully absurd about that image, isn't there? A cosmic bathtub with a floating planet. The universe has a sense of humour. But of course, Saturn is famous not for its density but for its rings. Those magnificent, breathtaking rings that make Saturn instantly recognisable, that have inspired wonder since Galileo first saw them through his telescope in 1610, though he didn't know what he was looking at first and thought Saturn had ears, or companion moons on either side. It wasn't until 1655 that Christian Huygens correctly identified them as rings. And what rings they are. Vast, thin, and made of billions upon billions of particles of ice and rock, each particle orbiting Saturn independently, all of them together forming structures that span hundreds of thousands of kilometers, but are only tens of meters thick in most places. The rings are impossibly thin relative to their diameter. If you made a scale model of Saturn's rings where the rings were as thin as a sheet of paper, Saturn itself would be the size of a large house. The rings are delicate, ephemeral, and yet they've existed for at least hundreds of millions of years, possibly much longer. There are several main ring groups, separated by gaps. The most prominent rings are called the A, B and C rings, with the Cassini division being a large gap between the A and B rings. This gap was discovered by Giovanni Cassini in 1675, and it's caused by gravitational resonances with Saturn's moons, particularly Mimas, which clears out particles in certain orbital paths. The rings are not uniform. They have structure, waves and ripples and gaps, braids and spokes, patterns created by gravitational interactions with Saturn's many moons. Some of these patterns are still not fully understood. The Cassini spacecraft, which orbited Saturn from 2004 to 2017, sent back incredible images of the rings, revealing details we'd never seen before, showing us just how complex and dynamic they are. And in its final act, Cassini dove into Saturn's atmosphere, burning up and becoming part of the planet it had studied for so long. It was a fitting end, a return to the world it had orbited for 13 years. The particles in Saturn's rings range in size from tiny grains like dust to chunks as large as houses. Most are made of water ice, nearly pure in some regions, though some contain rock and other materials. The ice is bright and reflective, which is why Saturn's rings are so visible and beautiful. They catch sunlight and shine brilliantly, creating one of the most iconic sights in the solar system. But the rings won't last forever. They're slowly falling towards Saturn, pulled by gravity and by interactions with Saturn's magnetic field. Estimates suggest the rings might only last another 100 million years or so before they're gone, falling into Saturn's atmosphere as a rain of ice and dust. 100 million years sounds like a long time, and it is, but it's brief compared to the age of the solar system. We're lucky to live at a time when Saturn has rings, when we can look up and see this spectacular display. It's a cosmic coincidence, a stroke of good fortune. Saturn rotates quickly, like Jupiter, completing one rotation in about 10.5 hours. This rapid rotation also makes Saturn bulge at its equator, and like Jupiter, Saturn has powerful jet streams, winds that blow at over 1,800 kilometers per hour near its equator, some of the fastest winds in the solar system. Saturn's atmosphere is banded like Jupiter's, but the bands are more subtle, harder to see, because a layer of haze obscures the deeper clouds. Still, Saturn has storms. It has a hexagonal storm at its north pole, a bizarre six-sided pattern of winds that has been stable for decades at least. No one knows exactly why it's hexagonal, why it maintains that shape, but there it is. A strange geometric feature on a planet of swirling gases. The universe is full of these oddities, these things that make you pause and wonder. The hexagon at Saturn's North Pole is enormous, with each side of the hexagon longer than the diameter of Earth. The storm rotates once every 10 hours or so, matching Saturn's rotation rate. Inside the hexagon, the atmosphere rotates as a coherent structure, like a jet stream bent into 6 straight sides. Outside the hexagon, the atmosphere has different flow patterns. It's a boundary, a dividing line, and it's perfectly stable. Scientists have created hexagonal patterns in laboratory experiments with rotating fluids, so we know it's a physical phenomenon that can occur naturally, but seeing it on such a massive scale on an entire planet is still breathtaking. Saturn has over 140 known moons, ranging from tiny moonlets embedded in the rings to massive Titan, Saturn's largest moon and the second largest moon in our solar system. Titan is bigger than the planet Mercury, and it's the only moon in the solar system with a thick atmosphere, thicker even than Earth's atmosphere. The surface pressure on Titan is about 1.5 times the pressure at sea level on Earth. Titan's atmosphere is mostly nitrogen, like Earth's, but it also contains methane and other hydrocarbons, and these create an opaque orange haze that completely obscures the surface when viewed from space. For centuries, we had no idea what Titan's surface looked like. It wasn't until the Cassini mission and the Huygens probe, which landed on Titan in 2005, that we finally saw beneath the haze. What we found was extraordinary. Titan has lakes and rivers and seas, but not of water. On Titan, it's far too cold for liquid water to exist on the surface. Instead, Titan has lakes and seas of liquid methane and ethane. It's the only other world in our solar system besides Earth that has stable liquid on its surface. It rains on Titan, methane rain falling from methane clouds, eroding the landscape, carving river channels, filling lakes. There are methane rainstorms and methane fog. There are dunes made of organic compounds, dark hydrocarbon particles blown into long parallel ridges by Titan's winds. The landscape looks strangely familiar in some ways, with river deltas and coastlines and lake shores, but it's made of entirely different materials. The rocks on Titan are made of water ice, which is as hard as stone at Titan's frigid temperatures of minus 179 degrees Celsius, and floating in Titan's lakes and seas are icebergs made of water ice, just like icebergs in Earth's oceans, but on Titan they float in liquid methane. It's a bizarre alien world, and yet it follows the same physical processes as Earth, just with different substances. It's a cold, dim, hazy place, but it's also one of the most fascinating moons in the solar system. A place where chemistry happens, where organic molecules are created and destroyed and created again, where perhaps the building blocks of life are forming in those hydrocarbon lakes. Not life as we know it, but something different, something adapted to the cold and the dark and the methane. Titan's largest sea is called Kraken Mare, and it's bigger than all of Earth's Great Lakes combined. It's located near Titan's North Pole, and it's filled with liquid methane and ethane. Radar data from Cassini showed that Kraken Mare is at least 300 meters deep in some places, possibly much deeper. Imagine sailing across a sea of liquid methane under an orange sky, surrounded by icebergs of frozen water. It's the stuff of science fiction, and yet it's real, happening right now on Titan, a moon of Saturn in our own solar system. Another fascinating moon of Saturn is Enceladus, a small icy world that's only about 500 kilometers in diameter. Enceladus is geologically active, with geysers erupting from cracks near its south pole, shooting plumes of water vapor and ice particles hundreds of kilometers into space. These geysers are powered by tidal heating from Saturn's gravity, similar to the process that heats Io, though much gentler. The plumes contain not just water, but also salts and organic molecules, suggesting that beneath Enceladus's icy crust, there's a global ocean of liquid water in contact with a rocky core. This is exciting because water in contact with rock can create chemical reactions that might support life. Enceladus is tiny, and yet it might be one of the most promising places to search for life in the solar system. The plumes make it easy to study too. Spacecraft can fly through them and analyze the material without even landing on the surface. Future missions to Enceladus are being planned, and they might answer the question of whether life exists in that hidden ocean. Saturn has many other moons, each with its own character. There's Mimas, with a giant impact crater called Herschel that makes it look like the Death Star from Star Wars. There's Iapetus, with one hemisphere bright white and the other dark as coal, a stark contrast that's thought to be caused by material from Saturn's outer moon Phoebe coating one side of Iapetus over millions of years. There's Hyperion, with a sponge-like appearance, its surface covered in deep pits and craters that give it a unique texture. And there are dozens of tiny moons embedded in the rings or orbiting just beyond them, shepherding ring particles creating gaps, influencing the structure of the ring system. Saturn's moons are a diverse collection, each one adding to the complexity and beauty of the system. Now let's continue onward, past Saturn, into the deeper reaches of the outer solar system where few spacecraft have ventured. The sun is smaller here, dimmer, and the cold is profound. Uranus is the 7th planet, from the sun, and it's an odd one. Uranus is an ice giant, smaller than Jupiter and Saturn, but still much larger than Earth. It's made mostly of water, methane, and ammonia ices surrounding a rocky core. What makes Uranus strange is its axial tilt. While most planets in our solar system have their axes tilted by a modest amount, Uranus is tilted by 98 degrees. It's essentially rolling around the sun on its side. Its poles point toward the sun at certain points in its orbit. Imagine that. For part of Uranus's year, one pole is in constant sunlight, while the other is in constant darkness. Each pole gets about 42 years of continuous daylight, followed by 42 years of continuous darkness, because a year on Uranus lasts about 84 Earth years. Scientists aren't sure why Uranus is tilted like this. The leading theory is that early in its history, Uranus was struck by one or more large objects, impacts that knocked it onto its side. It's been rolling around the sun like that ever since, a tilted world, unique among the planets. Uranus appears as a pale blue-green disk when viewed through telescopes. The colour comes from methane in its upper atmosphere, which absorbs red light and reflects blue and green light. The atmosphere is mostly hydrogen and helium, but that methane gives it its distinctive colour. Uranus is cold, so incredibly cold, with an average temperature around -224 degrees Celsius. It's not the coldest planet in the solar system, surprisingly. That honour goes to Neptune, even though Uranus is farther from the Sun. Uranus doesn't have much internal heat. Unlike Jupiter and Saturn, which radiate more heat than they receive from the Sun, Uranus radiates very little internal heat. It's a cold, quiet world, seemingly inactive, though recent observations have detected storms in its atmosphere, clouds moving at high speeds, suggesting that Uranus is not as serene as it appears. Because of its extreme tilt, Uranus experiences the most extreme seasons in the solar system. During the Uranian summer, the sun appears nearly overhead at the pole, and it stays there for 42 years. The pole basks in constant sunlight, though sunlight at Uranus's distance is very dim, only about 1/400th as bright as sunlight on Earth. During the Uranian winter, the pole is plunged into darkness for 42 years, receiving no sunlight at all. The equatorial regions experience more normal day-night cycles, but even there the sun's path across the sky is strange and unfamiliar, sometimes circling near the horizon, sometimes passing nearly overhead, depending on where Uranus is in its orbit. It's a world of extremes, of long, slow seasons that last for decades. Uranus has a faint ring system, discovered in 1977, and at least 27 known moons. Most of the moons are named after characters from the works of William Shakespeare and Alexander Pope, a departure from the usual practice of using names from mythology. The largest moons are Titania, Oberon, Umbriel, Ariel, and Miranda. Miranda is particularly interesting because its surface is a jumbled mess of different terrains, cliffs and grooves and cratered plains all mixed together. One feature on Miranda is Verona Rupes, a cliff about 20 kilometers high. If you stood at the top and jumped off, the low gravity of Miranda would cause you to fall slowly and you'd hit the bottom about 12 minutes later. Of course, you'd be going quite fast by then despite the low gravity, fast enough that the impact would likely be fatal, so it's not recommended. But it's a striking feature nonetheless, a testament to the strange and violent geological history of this small moon. Miranda's surface looks like it's been taken apart and reassembled, with regions of different types of terrain sharply juxtaposed. One region has grooves and ridges, another is heavily cratered, another is smooth and relatively crater-free. The leading theory is that Miranda was shattered by a massive impact at some point in its past, and then the pieces came back together under gravity, but they reassembled in a jumbled configuration. Or perhaps Miranda was partially melted by tidal heating early in its history, creating different types of terrain through geological processes, and then it froze solid when the heating stopped. Either way, Miranda is a moon with a complex history, a puzzle that we're still trying to solve. Let's journey now to the outermost of the classical planets, the last of the major worlds before we reach the small icy bodies at the edge of the solar system. Neptune is the 8th planet from the Sun, and it's the coldest planet in our solar system despite being closer to the Sun than Uranus. Neptune radiates more than twice as much heat as it receives from the Sun, and this internal heat drives powerful weather systems in its atmosphere. Neptune has the fastest winds in the solar system, with storms that produce wind speeds up to 2,100 kilometers per hour. That's faster than the speed of sound on Earth. The atmosphere of Neptune is active and dynamic, with giant storms that appear and disappear over years or decades. When Voyager 2 flew by Neptune in 1989, the only spacecraft ever to visit this distant world, it observed a large storm called the Great Dark Spot, similar in some ways to Jupiter's Great Red Spot. But when the Hubble Space Telescope looked at Neptune a few years later, the Great Dark Spot had vanished, replaced by a new storm in a different location. Neptune's storms are not as long-lived as Jupiter's. They come and go, born from the planet's internal heat and turbulent atmosphere. Neptune is a beautiful deep blue colour, even more intensely blue than Uranus. This is also due to methane in its atmosphere, but Neptune has a higher concentration of methane, making its blue colour richer and darker. Neptune is another ice giant, similar in composition to Uranus, with water, methane and ammonia ices surrounding a rocky core. It's far from the Sun, about 30 times farther than Earth, and sunlight at Neptune is about 900 times weaker than it is here. If you stood on Neptune, assuming you had a place to stand, the Sun would look like a bright star, much brighter than any star we see from Earth, but no longer the disk we're used to. It would be a point of light, and Neptune's sky would be dimly lit, a perpetual twilight. And yet, despite being so far from the Sun, Neptune has an active atmosphere, powerful winds and storms. It's a reminder that internal heat can drive weather just as effectively as sunlight, that the universe has many sources of energy, not just the obvious ones. Neptune's blue colour is striking and beautiful, and it's often described as the most purely blue planet in our solar system. The deep, rich colour is soothing to look at, calming, like looking at a clear ocean or a perfect sky. Neptune is cold and distant, but it's lovely, a gem floating in the darkness at the edge of our planetary system. Neptune has at least 14 known moons, the largest of which is Triton. Triton is unusual because it orbits Neptune in a retrograde direction, opposite to the direction Neptune rotates. This suggests that Triton was not formed alongside Neptune, but was captured by Neptune's gravity at some point in the past, probably from the Kuiper Belt, a region of icy bodies beyond Neptune's orbit. Triton is geologically active, one of the few moons in the solar system that shows signs of current geological activity. When Voyager 2 flew by Triton, it observed geysers erupting from the surface, plumes of nitrogen gas and dark material shooting up to heights of 8 kilometers. These geysers are powered by the weak sunlight reaching Triton's surface. Even at that distance, even with sunlight so faint it's enough to heat pockets of nitrogen ice beneath the surface, causing them to vaporize and erupt. It's a reminder that even in the coldest, most distant places activity can still occur, energy can still flow, change can still happen. Triton is slowly spiraling inward toward Neptune due to tidal forces. Its retrograde orbit means that tidal interactions with Neptune are causing it to lose orbital energy, and eventually, in perhaps a few billion years, Triton will cross what's called the Roche limit, the distance at which Neptune's tidal forces will overcome Triton's own gravity. At that point, Triton will be torn apart, shredded by Neptune's gravity, and its remains will form a magnificent ring around Neptune, a ring that might rival Saturn's in beauty. But that's billions of years away. For now, Triton orbits, geologically active, erupting geysers, slowly falling toward its eventual destruction. It's both a beginning and an ending, a story still unfolding. Triton's surface is young and varied, with few impact craters, indicating that it's been resurfaced relatively recently. There are regions of ridged terrain called cantaloupe terrain because it looks like the skin of a cantaloupe, with bumps and depressions creating a unique texture. There are frozen lakes of nitrogen ice, polar caps that change with the seasons, and a thin atmosphere that's mostly nitrogen. Triton is one of the coldest objects in the solar system, with surface temperatures around -235 degrees Celsius, and yet it's active, dynamic, fascinating. It's a captured moon, a visitor from the Kuiper Belt, and it's given us a glimpse of what those distant, icy bodies might be like. Now we've reached the edge of the classical solar system, the 8 major planets that orbit the Sun, but the solar system doesn't end at Neptune. Beyond it lies a vast region of icy bodies, remnants from the formation of the solar system, a sparse and cold frontier. The Kuiper Belt is a region that extends from about 30 astronomical units from the Sun, roughly Neptune's distance, to about 50 astronomical units. An astronomical unit, or AU, is the average distance from Earth to the Sun, about 150 million kilometers. So the Kuiper Belt is far away, incredibly far, and it's filled with small icy bodies, mostly made of frozen water, methane, and ammonia. These are objects that never coalesced into a planet, leftovers from the solar system's formation. They're sometimes called Kuiper Belt objects, or KBOs, and there are thought to be hundreds of thousands of them larger than 100 kilometers in diameter, and countless smaller ones. They orbit the Sun quietly, slowly, taking hundreds of years to complete a single orbit, cold and distant, rarely disturbed. The most famous resident of the Kuiper Belt is Pluto. Pluto was discovered in 1930 and was considered the 9th planet of our solar system for 76 years. But in 2006, the International Astronomical Union redefined what a planet is, and Pluto no longer met the criteria. it was reclassified as a dwarf planet, a decision that sparked a lot of debate and even some public outcry. People loved Pluto. It was small and distant and seemed like an underdog, the littlest planet, and there was affection for it. But the scientific community decided that there were many objects in the Kuiper belt similar to Pluto, and if Pluto was a planet, then so were dozens or hundreds of other objects. So new categories were created, and Pluto became a dwarf planet, the largest known dwarf planet in the Kuiper belt, a founding member of a new class of objects. In 2015, the New Horizons spacecraft flew by Pluto, giving us our first close-up look at this distant world. What it found was astonishing. Pluto is not a dead, boring ball of ice. It's geologically active, or at least it was very recently in geological terms. Its surface is young, with regions that have no impact craters, meaning they've been resurfaced within the past few million years. There are mountains made of water ice rising several kilometers high. There's a vast plain called Sputnik Planitia, a heart-shaped region covered in nitrogen ice that appears to be slowly convecting, turning over like a lava lamp. There are glaciers and dunes and possible cryovolcanoes. Pluto is tiny, smaller than Earth's moon, and yet it's active and complex and beautiful. The images sent back by New Horizons showed a world of variety and wonder, with a thin blue haze in its atmosphere, created by sunlight interacting with methane and nitrogen, scattering blue light just like on Earth. Sputnik Planitia is particularly fascinating. It's a massive basin, probably created by an ancient impact, and it's filled with nitrogen ice. The ice is divided into polygonal cells, each about 20 to 40 kilometers across, formed by convection currents in the ice. Warmer nitrogen ice rises in the center of each cell, flows outward, cools, and sinks at the edges, creating a slow, continuous turnover. This process is erasing impact craters, keeping the surface young and smooth. It's a dynamic system driven by internal heat from the decay of radioactive elements in Pluto's core. Pluto, so far from the Sun, so small and cold, is still geologically alive. It's a testament to the richness and complexity of our solar system, a reminder that even the most distant and overlooked worlds can surprise us. Pluto has 5 known moons, the largest of which is Charon, about half the size of Pluto itself. Pluto and Charon are tidally locked to each other, meaning they always show the same face to each other as they orbit their common center of mass. It's more like a double-planet system than a planet and moon. Charon has a dark red polar cap, thought to be made of organic molecules called tholins, created when methane from Pluto's atmosphere escapes, is captured by Charon's gravity, and is then irradiated by ultraviolet light from the sun. It's a complex chemical process happening in the cold and dark at the edge of the solar system, and it paints Charon's pole red. The universe is a chemist, constantly mixing and creating even in the most unlikely places. Beyond the Kuiper belt lies the scattered disk, a region of space where objects have highly elliptical orbits, taking them far from the Sun and then back again. And beyond that, even farther out, is the Oort cloud. Though we've never actually seen the Oort cloud directly, the Oort cloud is a theoretical spherical shell of icy bodies surrounding the solar system, at distances between about 2,000 and 100,000 astronomical units from the Sun. To put that in perspective, Pluto orbits at about 40 astronomical units from the Sun. The Oort cloud extends out to about a quarter of the way to the nearest star. It's incredibly distant, so far that objects there barely feel the sun's gravity, and they're easily influenced by passing stars and the gravitational tide of the Milky Way galaxy. The Oort cloud is thought to be the source of long-period comets, those comets that take hundreds or thousands or even millions of years to orbit the sun. Every once in a while, something disturbs an object in the Oort cloud, nudging it inward toward the sun, and it begins a long fall through the solar system, taking thousands of years to reach the inner planets, where it heats up and develops a tail and becomes a spectacular comet in our night sky. Comets are visitors from the edge of the solar system, messengers from the Oort cloud, bringing with them ice and dust from the earliest days of the solar system's formation. Speaking of comets, let's talk about them for a moment, because they're some of the most beautiful and mysterious objects in the solar system. Comets are sometimes called dirty snowballs, a somewhat unpoetic description for such lovely objects. They're made of ice, dust, and rocky material, and they spend most of their lives frozen and inactive, far from the sun. But when a comet's orbit brings it close to the sun, the heat causes the ice to sublimate, turning directly from solid to gas without passing through a liquid phase. This gas, along with dust particles, streams away from the comet, pushed by solar wind and radiation pressure from the sun, forming a tail that can stretch for millions of kilometers. Comet tails always point away from the sun, regardless of the direction the comet is moving, because they're shaped by the outward pressure of sunlight and solar wind. Most comets have two tails, actually. One is a dust tail, made of small particles that reflect sunlight and appear yellowish or white. This tail is curved because the dust particles have mass and follow their own slightly different orbits around the sun. The other is an ion tail, made of ionized gas that glows blue because of fluorescence. This tail is straight, pushed directly away from the sun by the solar wind. So a comet can have a broad, curved dust tail and a narrow, straight ion tail, both streaming away from the sun, creating a spectacular sight if the comet passes close to Earth and we can see it in our night sky. Comets are ancient. They've been around since the solar system, formed, preserved in the deep freeze of the outer solar system, largely unchanged for billions of years. When we study comets, we're studying pristine material from the solar system's birth, samples of the primordial cloud that formed the sun and planets, missions like Rosetta, which sent a lander to comet 67P/Churyumov-Gerasimenko in 2014, have taught us much about comets, their composition, their structure, their activity. Rosetta orbited the comet for 2 years, watching it as it approached the sun, observing as it became active, as jets of gas and dust erupted from its surface as its coma and tail developed. The lander, Philae, bounced across the comet's surface and came to rest in the shadow of a cliff, where it operated for a brief time before its batteries ran out. The data from Rosetta and Philae have given us incredible insights into comets, showing us that they're complex, dynamic objects, not just inert chunks of ice. Comets have played an important role in Earth's history. They've delivered water and organic molecules to our planet, perhaps contributing to the formation of our oceans and even to the origin of life. Every time a comet passes through the inner solar system, it leaves behind a trail of dust and debris in its orbit, and when Earth passes through these trails, we experience meteor showers. The Perseids, the Geminids, the Leonids, All of these meteor showers are caused by Earth passing through the debris trails of comets. The meteors we see are tiny particles, most no larger than grains of sand, burning up in our atmosphere as they collide with air molecules at high speeds. They're beautiful, these shooting stars, brief streaks of light that remind us of our connection to the cosmos. And every time a bright comet appears in Earth's sky, it's a reminder that our solar system is still dynamic, still active, still full of wanderers journeying from the distant reaches toward the sun and back again. Comets like Halley's Comet, which returns every 76 years, have been observed by humans for millennia, recorded in ancient texts and artworks. Comets were once seen as omens, harbingers of change or disaster, but now we understand them as natural objects following predictable orbits. Yet they still inspire awe, still make us look up and wonder. Let's drift back now, inward, toward the warmth of the inner solar system. We've journeyed far, out to the edge and beyond, and now it's time to return, to gather some final thoughts, some gentle facts to carry you into sleep. The solar system is 4.5 billion years old, formed from a cloud of gas and dust that collapsed under its own gravity. That cloud was set spinning by the conservation of angular momentum, and it flattened into a disk, with the sun forming at the center and the planets forming in the disk around it. This is why all the planets orbit the sun in roughly the same plane, why the solar system looks like a flat disk rather than a sphere. It's a remnant of that original spinning cloud, a memory of our origins preserved in orbital mechanics. Everything in the solar system is moving, orbiting, spinning, never still. Even objects that seem stationary are racing through space at tremendous speeds. The sun orbits the center of the Milky Way galaxy once every 225 to 250 million years. This is sometimes called a galactic year, or a cosmic year. Since the sun formed 4.5 billion years ago, it has completed about 20 orbits of the galaxy. 20 trips around, each one taking hundreds of millions of years. And with each orbit, the sun and its planets pass through different regions of the galaxy, through spiral arms and interstellar space, experiencing different environments, different levels of cosmic radiation, perhaps even different rates of comet impacts as we pass through denser regions of space. Our position in the galaxy is not fixed. We're travelers on a much larger journey than we usually think about. The planets orbit the sun in ellipses, not perfect circles. This was discovered by Johannes Kepler in the early 1600s, and it was a major breakthrough in understanding celestial mechanics. Kepler's laws of planetary motion describe how planets move, how their speed changes depending on their distance from the sun, how the time it takes to orbit is related to their average distance. These laws are elegant and mathematical, and they work not just for our solar system, but for any system of objects orbiting under gravity. Kepler figured this out using data painstakingly collected by the astronomer Tycho Brahe, observations made with the naked eye before telescopes were invented, measurements of planetary positions accurate to a fraction of a degree. From those observations, Kepler derived laws that still hold true today, laws that we use to navigate spacecraft through the solar system, laws that govern the motion of planets around distant stars in other solar systems. It's remarkable what the human mind can accomplish, finding patterns in observations, uncovering the underlying rules of the universe. Gravity is the force that holds the solar system together, the invisible bond between the sun and the planets, between planets and their moons. It's a weak force in some ways, much weaker than the electromagnetic force or the strong nuclear force, but it has infinite range and it affects everything with mass. Gravity is why you're pressed into your bed right now, why the moon orbits Earth, why Earth orbits the sun. It's why galaxies hold together and why the universe has structure. Gravity is curvature of space-time according to Einstein's general relativity. Mass tells space-time how to curve, and space-time tells mass how to move. It's a beautiful, elegant idea, and it explains not just orbits but also phenomena like the bending of light around massive objects, the slowing of time in strong gravitational fields, the existence of black holes. Gravity shapes the cosmos, and yet we can barely feel it. Just a gentle tug keeping us grounded, keeping us safe. The solar system is mostly empty space. If you were to scale down the solar system so that the sun was the size of a basketball, Earth would be the size of a small bead about 26 meters away. Jupiter would be about the size of a ping-pong ball 140 meters away from the basketball sun. Neptune would be over 800 meters away, and those are the major planets. The space between them contains almost nothing, just a few asteroids, some comets, some dust, and a lot of emptiness. The solar system is vast and lonely, and the planets are tiny specks scattered through that vastness. And yet those specks are connected by gravity, bound together, part of one system, one family. There's something comforting about that, about the idea that even across vast distances, we're connected to these other worlds, part of something larger. Let's think about the future of the solar system, far into the future, so far that it's almost impossible to imagine. The sun is about halfway through its main sequence life, the stage where it fuses hydrogen into helium in its core. In about 5 billion years, the sun will exhaust the hydrogen in its core and begin fusing helium. When this happens, the sun will expand into a red giant, growing so large that it might engulf Mercury and Venus and possibly even Earth. The sun's outer layers will extend far into space, and its surface temperature will drop, making it appear red. It will be a gentle giant, enormous and cool, but its expansion will be catastrophic for the inner planets. Earth's oceans will boil away, the atmosphere will be stripped off, and the surface will be scorched. If Earth is not engulfed by the sun, it will become a lifeless molten rock. But this is billions of years in the future, so far away that it's not something to worry about. By that time, if humanity still exists, we will have long since left Earth, spreading out to other worlds, other stars, or perhaps we'll have evolved into something unrecognizable, something we can't even imagine. The point is, change is inevitable, but it's also slow, so wonderfully slow, on cosmic timescales. After its red giant phase, the sun will shed its outer layers, creating a planetary nebula, a beautiful shell of glowing gas expanding into space. At the center will be the sun's core, a hot, dense remnant called a white dwarf. This white dwarf will be about the size of Earth, but incredibly dense, with a teaspoon of its material weighing several tons. It will no longer undergo fusion. It will simply cool down over trillions of years, slowly fading, eventually becoming a black dwarf, a cold, dark cinder floating through space. And the planets, what's left of them, will continue to orbit this stellar remnant, now distant and cold, receiving no heat, no light, just the faint gravitational pull from what the sun used to be. It's a melancholy fate, perhaps, but it's also peaceful. The end of a star is not violent, not for a star like the sun. It's a gradual dimming, a gentle fading into quiet. But that's so far in the future that it might as well be another universe. For now, for the next billions of years, the sun will shine, the planets will orbit, and the solar system will continue as it has for billions of years already. There's stability in that, reliability. The universe may be changing, but it changes slowly, patiently, giving us time to exist, time to grow, time to wonder. Now, let's slow down even more. Let our thoughts drift like dust particles in a sunbeam, weightless and free. Think about the light from distant stars, travelling for years or centuries or millennia just to reach your eyes. Every photon carries with it a story, a message from the past, from a star that might no longer exist but whose light is still on its way, still travelling, patient and constant. Think about the fact that you are made of atoms forged in the cores of ancient stars, stars that lived and died billions of years ago. The iron in your blood, the calcium in your bones, the oxygen you breathe, all of it was created in stars, scattered into space when those stars exploded, and eventually incorporated into the cloud of gas and dust that became our solar system. You are literally made of stardust. You are the universe experiencing itself, a collection of atoms that have become aware, that can look up at the night sky and recognize their origins. And in that night sky, there are more stars than you could ever count, more galaxies than you could ever visit, more worlds than you could ever imagine. And yet here you are, on this one world, in this one solar system, in this one corner of the universe, resting comfortably, safe and warm, connected to everything, and yet entirely unique. The solar system is your home on a grand scale. Earth is where you live, but the whole solar system is your neighborhood. The sun warms you, the moon lights your nights, the planets orbit silently in the darkness, and all of it has been here long before you and will be here long after you're gone. There's comfort in that permanence, in that continuity. The universe is patient and enduring, and you are part of it. A brief flicker of consciousness in an ancient cosmos, but no less important for being brief. As you drift towards sleep now, imagine yourself floating through space, weightless and serene, passing by planets and moons, seeing them up close, feeling no fear, only wonder. Imagine the sun in the distance, warm and bright, a constant companion. Imagine the stars surrounding you, countless points of light in the darkness, each one a sun with its own system of worlds, each one a story waiting to be told. And know that wherever you are, whatever happens, you are part of this grand cosmic dance, this ballet of gravity and light and time. You are stardust, ancient and precious, existing for this moment, this brief and beautiful moment. And that is enough. That is everything. Rest now. Let your breathing slow. Let your body relax into your bed, supported by the solid earth beneath you, the earth that has been here for billions of years and will be here for billions more. Let the stories of the solar system carry you gently into sleep, and when you wake, the sun will still be shining, the moon will still be orbiting, and the universe will still be here, vast and beautiful and patient, exactly as it has always been. Good night, my friend. Sleep well. The stars will be here when you wake, and the solar system will continue its eternal dance, indifferent to our worries, majestic in its simplicity, a reminder that we are part of something much, much larger than ourselves. Sweet dreams. May you float peacefully through the cosmos tonight, visiting distant worlds, seeing wonders beyond imagination, and may you wake refreshed, knowing that you are connected to all of this, to the sun and moon and stars, to the planets and comets and asteroids, to the very fabric of space and time itself. You are the universe, and the universe is you, and there is nothing to fear, nothing to worry about, only endless wonder waiting to be discovered. Rest now, dear friend. The cosmos watches over you. Sleep deeply and peacefully,